So last time we learned about the matchings in bipartite graph. We proved the Hall theorem, and then we proved the relationship between vertex cover number and matching number. Now we want to talk about the matchings in general graphs. So not necessarily bipartite graph. If we want to prove something like Hall theorem for general graphs, then the obvious immediate try we want to do is again try to compare with the neighborhood of S and then S and their size difference. However, if you think about it, you can consider the following example, say complete graph on 2n plus 1 odd number of vertices. In here, this is one of the graphs there, the n of S is as large as it gets for any subset. So complete graph is the one that the neighborhood of any set is as large as it gets. It's everything. Okay, technically if S consists of only one vertex, it's everything except that vertex. But this is the, most ideal graph to find matching. You can match any two pair. However, it does not have a perfect matching. So situation is a little bit more different for general graphs than bipartite graph. And you might see from here, another factor that we have to consider is parity. So for bipartite graph, this phenomena was not there, but here we have to consider somehow parity issue. For this one specific graph, it doesn't have a perfect matching, but we have a matching which is almost perfect. A matching that misses one vertex. But more generally, we can take the disjoint union of odd clique. Then we can find the example whose matching number is quite lower than the order of the graph divided by 2. So we want to study about matchings in general graph, and then somehow this parity matters. So we will define some terminology which will help us to discuss about the relationship between matching numbers in general graph and this parity issue. So first, we want to define a concept which is more general than perfect matching. Let's say we have a certain number k, and we say k factor in a graph G is a k regular spanning subgraph. Of G. So perfect matching is a spanning subgraph, which meets every vertex. So disjoint union of edges, which meets every vertex, which means it is a one regular spanning subgraph. So this is a more general concept than perfect matching. And we say that an odd component of a graph to be a component of odd order. A component of the graph which consists of the odd vertices. And we write small o of G to denote the number of odd components of G. With this, now we discuss about the matchings in general graph. So our benchmark is again Hall's theorem. We want to prove something like Hall's theorem. What was the Hall's theorem? In Hall's theorem, what did we do was for each set, we consider this quantity. And this is the quantity that has to be missed by the maximum matching. If this is positive for certain set S, which is subset of X, then some vertex has to be missed. And let's consider this again. But now we want to be more careful about parity. So if we have a certain theorem for general graphs, then that should also apply to bipartite graph, right? Bipartite graph is a smaller family. So if you want to prove certain theorem, which is something like Hall theorem, then that theorem has to be more general than Hall theorem. So hopefully it should also apply to bipartite graph and give the same conclusion as the Hall theorem. So we want to see what's missing on this quantity. We want to find the same corresponding quantity for general graph, which has the same meaning as this in the bipartite case. So what's happening? So you have a, say, S here, and you have a neighborhood of S, and possibly there are edges here and here and here and here. So no edges between these two. Then here, I mean, if this one is smaller than this one, some vertices here has to be left out. They remain unmatched. So that's the obstacle for obtaining perfect matching. And then we actually show that if we choose the optimal S, ideal S, then that exactly covers how many vertices have to be unmatched in the maximum matching. So now what we do is we consider this set as T. And what's happening is that if we consider G minus T, then what do we get? We have this S, and T is completely deleted. Then what do we know? All the vertices here in S becomes isolated. And possibly, I mean, these are connected, but if T is deleted, then let's say, wait. Yeah. Yeah, let's say this is the picture. So T is deleted, so all the edges attached to T is gone. So these are isolated vertices. But if you think about it in disparities point of view, these isolated vertices are odd component. Even if, say, we have instead of isolated vertices, if we have some odd component here, say K3, three vertices. Still, what do we know? I mean, still, if there is like two here, and then four components here, we know that at least two of the components, I mean, no matter how you take a perfect matching, two vertices are left out, or here, and then here, again, two vertices are left out. So the crucial point of the crucial reason why we couldn't get perfect matching was not because of this was just isolated vertices, but the essential reason was this was odd component. The odd component, if you want to cover everything, then one has to be matched with T and one has to be matched with T. Then something are left out. Based on this, I mean, so, so this kind of suggests that this quantity was actually the number of odd components in G minus T minus size of T. So they were same when T was discrete. So maybe, yeah, that was more crucial quantity. So, I mean, if we, instead of trying to measure the matching number, if we just care about the perfect matching, then what's the necessary condition that we get from here is that for having perfect matching is that if G has one factor perfect matching, then for any vertex set, G minus S must have at most size of as many odd components. As we discussed here, if you have a S and then there are odd components, and if there are only three of them or four of them, then it matches at most four of them, leaving this one odd component. I mean, at least one vertex from here are not matched in any matching, so there are no perfect matching. So again, we can show that this necessary condition is also sufficient, which gives us the following Touch theorem. So Touch one-factor theorem says that a graph G has a one-factor, the perfect matching, if and only if what happened? The number of odd components in G minus S is smaller than S for all vertex subset S of G. Again, we can prove further than this. Not just we can find the formula for the matching number, which is more general this theorem. Just like we did for Hall theorem. We proved Hall theorem and then we find the formula for the matching number in bipartite graph. We can do the same, and then there, the key quantity is this. So we want to give name to this quantity to facilitate our discussion. And we say we give the name of deficiency, and we write f of S of a vertex set S in a graph G is you take out the vertices inside of S, and then in the remaining graph, you count the number of odd components, and then you subtract the size of S. Again, this quantity, if you maximize it, then it gives you the exactly how many velocities is in the graph has to be not matched in the matching, in the maximum matching. That gives you this theorem, which is called Berge Tutte formula. So matching number of G is same as minimum out of all vertex set. You take half and you take the n minus deficiency of x. S. So you want to maximize this, then you want to minimize this. So this is the number of vertices. This is the number of vertices that's not matched by the maximum matching. So this is the number of vertices that's matched by the maximum matching. Now we want to count the number of edges instead of the vertices. So you divide it by 2. So as this Berge-Tutte formula is stronger than this Tutte theorem, so this is implied by Berge-Tutte formula. So we only have to prove the Berge-Tutte formula. We want to prove the Berge-Tutte formula. And before proving that, let's collect some lemma. Say if, so first lemma is about the parity of this deficiency, which will be useful later for our proof. If S is the set of vertices in on n vertex graph G, then this deficiency has same parity as n. And proof is easy. Why? This is actually has same parity as G minus S plus S, because 2 times S is same as 0 in modular arithmetic. We are doing arithmetic in modular 2. And then this is actually same as n, because what? You have odd components. Instead of counting 3, you just count 1. Instead of counting 5, you just count 1. Instead of the odd number, you count 1, and then here you count every vertex in that. That's counting every vertex in here. And here is just you count the even times less. So this is trivial lemma. And let's take another lemma. And this lemma gives us the property about the set T, which is a maximal set with maximum deficiency. So what it means is that you take all the sets which have the maximum deficiency. And out of that, let's say this set has the maximum deficiency and this set also have the maximum deficiency. Then we take this one. Because, so this maximal set means inclusion maximal. If we take T, there are no other set, T prime, which completely contain T and having the maximum efficiency. So if no such set exists, then this is the maximum set. It's also okay to take this set as long as there are no other set completely contain this. This maximum set does not have to be maximum set, which is the largest set, the inclusion maximum. So, and we want to study about the property of this. Because our proof later we will prove this Berge-Tutte formula using inductive argument. Just like we did for the whole theorem, we take specific, for whole theorem, what what did we do? We take specific S, whose neighborhood set is, have the same size as S. And then that partition the graphs into two, and then there you find the matching in each of one of them. Here, what we want to do is we do the similar way, philosophically similar way. We will take such a set T with the maximal set with maximum deficiency, and then see how the graph structure looks like, and then we try to apply inductions on this structure. So then what can we conclude? If U is a vertex of odd component, say C of G minus T, then C minus U satisfies Hutch condition. Here, Hutch condition is this. So also, this G minus T has no even components. Even component means components with even number of vertices. So let's prove this. So what do we know? We have T, and then we have C, and then another odd component here. And we have, say, one vertex U here. Then what we want to prove? We want to prove that this part satisfies touch condition. So we have to consider the set S here. For S in the vertex set of C minus U, what do we want to do? We want to count the number of odd components of what? C minus U minus S, right? So you take, say, S here, and then once you take this out, you have certain odd component. Then you can see that this is actually also odd component in the original graph if you delete this. Yeah, of course, you delete this and then delete this, then this is the odd component. And so what do we get? Okay, let's just write these are contained in C minus U. Then what? Deficiency of the original graph of T union with S union with U. You take the deficiency when you take out this set. So what do we know? This set is a set containing T. And then our assumption was this is the maximal set with maximum deficiency. So this has a strictly smaller deficiency than T. But what do we know? Out of all odd components, when we in G minus T, these are still kept there while one disappeared. So what we have to write first is number of odd components in G minus T minus S minus U minus 1 are the number of components here. Give me a moment. Let's not write this. Let's write it this way. So by the definition, this is same as minus t minus s minus 1, right? But what do we know? So here, number of odd components, once you delete this, is the number of odd components in g minus t minus 1, which is counting these two. And then we have to take the addition of c, number of odd components in c minus s minus u. And we have this t minus s minus 1. Then what do we get? These two parts give us the deficiency of t. Then these two give us minus 2. And the other two give us efficiency of c minus u in s. Efficiency of s in c minus u. Then what we have this. So as we wanted to say, this assumption says that this has to be smaller than this. So this has to be inequality. But here, from there, what do we get? This shows that, this and this and this. Then this shows that this deficiency is at most 1. Because this has to be strictly smaller than that. And this is at most 1. But what we wanted was, this was at most 0. We want to say that this deficiency was never positive. So we are 1 short. But what do we know? We have this previous lemma that kind of boosts our inequality. What do we know? Since C minus U has even order, its deficiency of C minus U is even by the previous lemma. Thus what? This is even. So if S as a positive deficiency, then it has to be at least 2. Then we get the deficiency of G, T union S union U is bigger than or equal to deficiency of T, or contradiction to the choice of T. So we conclude that the deficiency of S in C minus 3 is as non-negative for all S in this C minus U. Such condition holds. So this proves, the first bullet point, first part. And we want to also prove the second one. Second one is easy. If T has here odd component, and then even component, then what do we do? We can take the union with these two. Then this is the set contains T. Then the efficiency is same, the number of odd components. No, sorry, I was wrong. You take this set. You add one vertex to T, then T gets 1 larger, you get a 1 more odd component, so deficiency is same, and you get a bigger set. So if G minus T has an even component, say C, then adding to T, say any leaf of a spanning tree 없이. So in order to, avoid the complicated situation, so C is a connected component, so it contains a spanning tree. You take one leaf and then you just add it to T, then the remaining thing is still a component, still connected. So it is still a component. This creates a larger set with the same deficiency. Hence, this is a contradiction to the choice of T, so hence G minus T has no even component. So now we are ready to prove the Berge Tutte formula. So what do we have to show? So first, proving one direction, this inequality is easy, right? So we only have to, so it is enough to construct a matching of size half of n minus efficiency of G. Did we define the deficiency of G? We didn't define. Let's say deficiency of G is the maximum deficiency of S. So again, we use induction on N, number of vertices. And yeah, of course, consider N is positive. Otherwise, there is nothing to prove. And again, our plan was take the set T, which is a maximal set with maximum efficiency, say D. Then what do we have? We have T, and then we have certain odd components. By the previous lemma, G minus T has no even components. And C minus U satisfies Tutte condition. For all odd component C of G minus T and a vertex U in this C. Then what do you know? This C is a graph smaller than G. Yeah, why? If T was empty set, then there was nothing to prove. Give me a moment. If T was the yeah, if T was the empty set, and this satisfies the touch condition, then you apply the apply the induction hypothesis in this, the C is same with G. If T was empty set, C and G are the same. You take out the one vertex set, then the remaining one is still a smaller one. So no matter whether T is empty or non-empty, it doesn't matter. This C minus U is always a graph smaller than G. And then it satisfies touch condition. So by induction hypothesis, it contains a perfect matching. So C minus U contains a perfect matching for all such C and U. Then what do you know? Then what? Now you just have to find the matching between this T and here. Because in that case, the remaining one contains perfect matching. And here perfect matching with one vertex missing. Then that already gives us a matching that misses exactly D vertices as desired. So we only have to cover T using, say, size of T edges to size of T many distinct components of G minus T. So what do? Now our goal is you have vertices. Then you want to find the matching covering this and this and this. Covering all the vertices here. That's actually very similar situation as what we dealt last time. It's matching in bipartite graph. So you can apply Hall theorem there. So what do? So we consider here T, and then here we have the component. And instead of components, let's say you consider this artificial set Y, let Y be the set of all T plus D components. All of them are actually odd of G minus T. So for each odd component, you put the one vertex here. And to obtain the desired matching covering T, we consider an auxiliary TY bigraph, say H. And we say that let H have an H, say TY, for T inside of T and then Y inside of Y, if and only if T is adjacent in the original graph G to any vertex, some vertex of the component of G minus T corresponding to this Y. Then what's our goal? We wanted to find the matching here covering all the vertices in T. That's same as finding matchings here, which covers all the vertices in T in this auxiliary graph. Because once we have a edge here, that means there is one edge from here to some vertex here. So we just take it, and we just take it. Then that's what we get. For that, we need to check the Hall's condition on this bipartite graph. So for any set S, which is subset of T, we want to show that its neighborhood set is larger or equal. So what do we know? All vertices of this Y other than those in the neighborhood of S. So what do we know? You have T, and then you take some S. And you have this odd component. And then neighborhood of S are the odd components here. So, and there are no edges between here and here. The odd component. And then we have some edges here and here. Here. Then what happened? If we delete this, then these are odd component, and then this actually merges with S, right? So all the vertices in Y, other than those in here, so this corresponds to this odd components. They form odd component of G minus T minus S. Then what do we know? By the maximality of T, we have that the deficiency of T minus S in graph G is M most D, because D was the deficiency of T, right? Then what do we know? This deficiency is what? That's this is the number of odd components. So here S with the neighborhood forms one component, and then these are all odd component. So these odd components are exactly the Y minus the neighborhood of S here. So this is 2, meaning that this is 2. So that's the number of odd components, and then you subtract these two. And so this is actually at most this deficiency. Deficiency could be one larger if this is also odd component, but this is certainly a lower bound. And this is at most what, D. Then what do we know? But Y was actually same as T plus D. The number of vertices in T plus the deficiency was exactly the number of odd components. Then what? What do we get? So this minus this is S, this cancels out. So you get this. So by Hall's theorem, so this shows that this auxiliary graph satisfies Hall's condition. So Hall's theorem, H has a matching covering T. And it shares its edges. Here the desired matching covering T in G. Then, yeah, this, provides this matching. And then in the remaining one, you apply this induction hypothesis to find the perfect matching here, perfect matching here, perfect matching here. And then in the remaining one, you take arbitrary vertex out. And then in the remaining one, you take the perfect matching, perfect matching, perfect matching. then you obtain the matching of the desired size. So this proves the Berge Tutte formula. And yeah, in the next video, we will try to talk about this more general factor. So we define this K factor, and then we just have talked about one factor. What if we want to find the more general factor, then what should we do? That's what we will talk about in the next video.